So today we're going to continue with our triangles module by talking about two special types of triangles. Today we are going to cover isosceles triangles and equilateral triangles. So our main objective for today is that we're going to be able to solve for missing angle and side measures in both isosceles and equilateral triangles. That's going to involve a couple theorems that we're going to be talking about. We're going to be talking about the base angles theorem, we're going to be talking about the converse of the base angles theorem, and some corollaries as well. Now, for your mastery ticket today, you're going to have two questions. One is going to involve isosceles triangles, and one is going to involve equilateral triangles. So by the end of class today, you will be able to set up and solve for x in each one of these triangles that we have here. So up at the top of your first slide here, you have four examples of some real-world isosceles and equilateral triangles, and we're going to talk about today why each one of these would fit into the category of an isosceles and an equilateral triangle, or an equilateral triangle. But we have the pyramids in Egypt here. We have this figure, it's just a piece of art. You have your yield sign, and then you have your triangle for the pool table. Now, the first thing that we are going to talk about, or the first type of triangle that we're going to talk about today, is what is called the isosceles triangle. And an isosceles triangle is basically a triangle with two congruent sides. And we know that the word congruent means equal. So you will notice on this figure that we have here that these two sides are marked as being congruent. Remember that these are your congruence markings here. These little hash marks say that those two sides are the exact same size. Now, there are a couple vocabulary terms that you do need to know about the isosceles triangle that we're going to talk about today. So I want you to pause the video and take a minute and copy down this figure here. And when you're done copying it down, you can start up the video. We're going to talk about what each one of these means. So you should have your figure copied down by now. And in our figure here, in the isosceles triangle, there are two congruent sides. Those two congruent sides are what we call the legs. That third side that is not congruent to the other, and I'm not sure why this isn't marked on here, but this is our base right here. So you have two legs and a base. Then you have three different types of angles. You have two base angles, and the two base angles are in between the leg and the base, so they are the two angles that are basically attached to the base of the triangle. And then you have your vertex angle, which is up at the top of the triangle here. It's not necessarily always at the top, but the vertex angle will always be in between the two legs. Then up at the top, this is your vertex point up at the very top of the triangle here. The vertex point is always wherever your vertex angle is, and it's where the two legs will meet. Now, the first theorem that we are going to talk about today is what we call the base angles theorem, and the names are not as important as being able to understand what they represent. So in our base angles theorem, and I'm going to give you a second to copy this down, I'm going to have you pause the video after I explain this, but I want to explain it real quick and then we'll move into the example. But what the base angles theorem says is that if two sides of a triangle are congruent, so if these two sides right here are congruent, then the angles that are opposite those two sides are congruent as well. So basically, if you have two congruent legs in an isosceles triangle, then you will have two congruent base angles as well. Remember, the two base angles are the two angles that are along the base or the non-congruent side there. So I'm going to give you a second to go ahead and copy down this theorem, and then we're going to move on to example 1. So go ahead and pause the video, and when you're done copying, you can start it right back up. Alright, so let's take a look at example number 1. And in this example, it asks us to solve for y. Now, what I can tell in this first example is that I definitely have an isosceles triangle because these two sides are being marked as congruent. So that means these are my two legs right here. Now, what the base angles theorem says is that if you have two congruent legs or two congruent sides, that the base angles that are opposite those sides will be congruent as well. So you will notice that these two angles right here are opposite our legs. So these angles right here are the base angles that we are referencing up here. So instead of being at the bottom of the triangle, they are actually at the top because our isosceles triangle has actually been flipped over. So this is our base at the top, these are our two legs, and our vertex is down at the bottom this time. Now, what our base angles theorem says is that those two angles should be congruent. Well, they definitely are congruent. They are both 50 degrees. So what we are trying to solve for in this case is our y value. Now, there is another piece of information you're actually going to need to solve this problem, and that piece of information that we need is the fact that a triangle will always add to be 180 degrees. We talked about that just in our lesson on Friday of last week, and if you made up some work, you looked at that yesterday. So if we know that the angles of a triangle are always going to equal 180 degrees, we can write an equation where we add these three angles together. So I have y plus 50 is always going to equal 180 degrees because the three angles in any triangle is always 180 degrees. Now, once I get to this point, I want to solve my equation. So over on the left-hand side, I notice that I have some like terms that can be combined. So I have y plus 100 is equal to 180. Then I'm going to subtract that 100 to the other side. And I end up with y is equal to 80 degrees. Now, you will notice in this problem that we didn't specifically use the base angles theorem. We showed the base angles theorem by showing that these two angles were in fact congruent because they were opposite those sides right there. So we kind of just verified it. But you will see in this problem how we are pulling in the other triangle theorems in order to solve our problems. So just because we finish with the section doesn't mean that that theorem's not going to come up again. When we are working with triangles, the theorems will always overlap. Now let's take a look at number 2. In number 2, we're asked to solve for x and for z. Now, in this triangle here, what I notice is I definitely have an isosceles triangle because these two sides are marked as being congruent. Therefore, these are my two legs. Now, what the base angles theorem tells me is that the angles that are opposite those sides are also going to be congruent as well. Those are our base angles. So this is our base right here because it is the non-congruent side. So the x and the z are both our base angles. Now, what that theorem says is that those two base angles are going to be congruent to each other. So I know that both of these angles are exactly the same size. I also know from algebra that I can only work with one variable at a time. I cannot work with an x and a z at the same time. But if I know that these two angles are exactly the same size, I want to call both of them x because I know that x is equal to z. Whatever x is, z has to be the same thing. So what I'm going to do is I'm going to use x for both of these angles right here. You could have used z if you had chosen to. If you wanted to use z for both of these angles, it would have been fine. I just usually use x because that's what we're used to. Now, once I have these two variables being the same, I can now work with this problem. Now, I'm going to go back to what I said a second ago, that I have three angles in a triangle. So we are going back to our triangle angle sum theorem, which says that the three angles in any triangle are always equal to 180 degrees. That theorem is never going to leave you. It's going to come up multiple times in this class. So kind of keep that in mind, that whenever you have a triangle, that key number that we're thinking is 180 degrees. So I'm going to add my x plus my 60, and I'm going to set that equal to 180. Once I do that, I see I have a set of like terms here that can be combined, and I have x plus x is 2x plus 60 is equal to 180. I'm going to subtract that 60 to the other side, and I end up with 2x is equal to 120. Divide both sides by that 2, and I end up with x is equal to 60 degrees. Now, we also know that x and z are equal to each other, so I also know that z is equal to 60 degrees as well. Now, what you will notice in this triangle is this angle is 60 degrees, this angle is equal to 60 degrees, and this angle is equal to 60 degrees. So not only are the two base angles congruent to each other, but all three angles in this triangle are actually congruent to each other. We're going to talk about what type of triangle that is, but it's not only isosceles, we're going to talk about in a second that it's also equilateral as well. Now, the next theorem that we're going to talk about, and I'm going to give you a second to copy this down. I'm going to have you pause the video. But this theorem is the converse, and converse means opposite, basically. So when you're working in the opposite direction of a theorem, that is what we call the converse. So the converse of the base angles theorem basically works in the opposite direction. So what this theorem says is that if these two angles here, these two base angles are congruent, then the sides that are opposite those two base angles are congruent as well. So basically what we're learning in this section is that if you have an isosceles triangle, not only are the sides congruent, but the angles are congruent. And not only are the angles congruent, but the sides are congruent. So this theorem works in both directions. So it's a kind of a vice versa type thing here. So our sides and our angles are going to be congruent in this figure. So go ahead and take a second to copy this down. You can pause the video, and when you're done, start it right back up, and we'll go on to our next set of examples. Now, in this set of examples, I'm going to kind of get you set up with some of these, and then I'm going to have you solve these equations by yourself, because this is basically taking some geometry and adding some algebra in there, and I know you all know how to solve equations, so I'm going to leave you to solve for some of these. If you need some help, we can work one-on-one, but I want to help you get these set up first. So in example number 1, it asks us to solve for x, and what it tells us is that these two angles right here are congruent to each other. Well, what the converse of the base angles theorem says is that if you have two congruent angles, then the sides that are opposite from those angles are congruent as well. So I know that these two sides that are opposite are congruent to each other. So that's why I marked them with these little hash marks here. So if those two sides are congruent, what the word congruent means is that they are equal to each other. So if I know that these two sides are equal to each other, then I can set them equal to each other. So I'm going to take 2x minus 15, and I'm going to set it equal to 9. Now, this is the point where I'm going to start leaving the problem for you to solve from here. So what you want to do is you want to work through this example, get your values to the other side, and figure out what x is equal to. So you are going to finish solving this equation on your own. It may require you to pause the video for a second and then come back. Some of you may have already solved this by the time I finish talking. So let's take a look at number 2. Exact same thing in number 2. We have two congruent base angles right here, and we know that two congruent base angles mean that we have two congruent sides as well. So we know that these two sides right here are congruent to each other, and we know that the word congruent means equal. So we are going to take our two sides and we are going to set them equal to each other. Now, once you get your equation set up, you know you need to get your variables over to the left-hand side. You know you need to get your numbers over to the right-hand side. So you are going to go ahead, go through this process, figure out what x is equal to. If you have any questions, please ask either Miss Tucker or myself, and we will be happy to help you. I want to give some of you a little bit of practice and a little bit of freedom to actually use these skills, but if you are struggling, please let us know. We are always happy to help. Next up, the second type of triangle that we're going to talk about is the equilateral triangle. And a lot of the things that we talk about with the equilateral triangle are going to be very, very similar to the isosceles triangle. There is one major difference between the two of them. Now, first of all, let's talk about the basic definition of an equilateral triangle. Basically, an equilateral triangle is a triangle with three congruent sides here. So you will notice that all three of these sides are marked as being congruent. Now, one of the two theorems that we are going to talk about that deals with equilateral triangles, and we call it a corollary because a corollary is basically an extension of a theorem. So this is an extension of the base angles theorem. Now, what the base angles theorem said was that if you had two congruent sides, that your two base angles would be congruent as well. The extension with the equilateral triangle is that if all three of your sides are congruent, then all three of your angles should be congruent as well. So it's not two sides and two angles this time, it's three sides and three angles instead. So that's the extension here. Now, the major difference that you are going to see is going to occur in this second bullet right here. There is a very, very special property that applies to equilateral triangles only. So what we're going to talk about is what are the measures of the angles in an equilateral triangle always. This is always, always, always going to be true. Well, let's think about what the measures of the three angles in any triangle are. We learned back the other day that the measures of the three angles in any triangle is 180 degrees. If I know that all three of these angles are exactly the same size, I can divide that 180 between the three angles that are in that triangle. So if I divide 180 by 3, I end up with 60 degrees. So that means that this angle has to be 60 degrees. This angle has to be 60 degrees, and this angle has to be 60 degrees. That is a property of equilateral triangles only. All three angles in an equilateral triangle will always be 60 degrees. So in one of our previous examples, I was telling you I'm going to explain to you why this triangle is equilateral. Now you know why it is equilateral, because we found that the three angles in that triangle were 60 degrees. So what we're going to do in these two examples, and I'm going to do something very similar to what I did in the previous problems, that I'm going to set up the equation for you, and I'm going to leave you to actually solve that equation. But in these two examples, we're going to use that corollary that we just talked about. And what we know in these two figures that we have here, I notice that these triangles are marked as being equilateral. All three sides are congruent here, and all three sides are congruent here. Therefore, I know something very special about each one of these triangles. I know that every one of the angles in both of these triangles is 60 degrees. So I'm going to go ahead and label all three of those angles 60 degrees. Now, I am asked to solve for x and for y. I know I cannot solve for two variables at the same time, so I know that this is going to actually require two different equations. One for the x and one for the y. So let's set up our x equation first. Now, I know that this angle is 60 degrees, and I also know that this angle is x plus 5 degrees. So I know that these two values should be equal to each other because they are the same angle. If this angle is 60 degrees, then x plus 5 has to equal 60 degrees. Now, once you have that equation set up, you're going to go through, do what you need to do, and you're going to figure out what x is equal to here. Now, let's do the same thing. Let's set up an equation for y. Once again, because I know that this angle is 60 degrees, I know that y minus 10 has to equal 60 degrees. So that's what I'm going to do. Y minus 10 is equal to 60 degrees. I'm going to go through, do my thing, and solve for y and figure out what y is equal to. So you're going to solve these two, one for x, one for y. Now let's take a look at number 2. Pretty much the exact same thing in number 2. We have two angles that are marked with x's and y's, and we want to go through and we want to solve for that x and that y. Once again, we know that each angle is equal to 60 degrees, so we're going to take our expressions that we are given here and we're just simply going to set them equal to 60 degrees. So the first one is going to be 2x is equal to 60 degrees. And I'm just going to go through and solve this one because it's so easy. We'll divide both sides by 2. So we know that x is equal to 30. And then I'm going to do the same thing for the y. I've got 3y is equal to 60. Divide by 3, and we get y is equal to 20. Now, last theorem that we are going to talk about is basically working in the opposite direction. And this one is pretty much common sense after everything that we've done. We've talked about the fact that every time you have congruent angles, you have congruent sides. Every time you have congruent sides, you have congruent angles. So what this theorem here says, and it's the corollary to the converse of the base angles theorem, a very confusing name, which doesn't really matter. But what this theorem basically says is that if a triangle is equiangular, and equiangular means that all three angles are congruent, then it is equilateral. So all this theorem is saying is that if you have three equal angles, your three sides are going to be equal as well. That's just common sense. We've talked about that. Congruent angles lead to congruent sides lead to congruent angles. So that's pretty much the summation of all four of our theorems that we've talked about today. You will notice that there is a huge overlap between all four of these theorems. All right, so our last set of examples, we're almost there. In our last set of examples, and there's some markings missing from the second triangle. Let me add these in real quick. These angles right here should be marked as being congruent. I don't know why they aren't, but those angles should be marked as being congruent. All right, so let's take a look at our two examples. So what we notice in our two examples that we have here is that all three angles are marked, or should have been marked in this case, in our triangles, which means that all three sides are congruent as well. So we know that this is an equilateral triangle. We know that this is an equilateral triangle as well. Now, what we know about an equilateral triangle is that all three sides are congruent, meaning that these two sides are exactly the same size. If they are exactly the same size, then they are equal to each other. So that's all we're going to do is take these two pieces and we are going to set them equal to each other. Now, once you do that, and again, I'm going to leave this for you to solve because you know how to solve equations by now. So you are going to go ahead and solve for x. Now, the last problem that we have here is a little bit tricky because you will notice that all three of the sides are marked and all three of them have X's on them. So which set do we use? Do we try to use all three? How do we do this? When you are looking at this triangle here, first of all, you cannot use all three of them at the same time. There is only two sides to an equation, the left and the right. So you can only use two of these sides at a time. Now the second question is, does it matter which two sides I use? No, it doesn't. This is an equilateral triangle. All three are the same. Now, if it were me, I would choose the easiest of the sides. I would choose to use these two sides right here because they're the smallest expressions. They have the smallest numbers in them. This has a 3 and a 9. This only has an x and a 9 and a 2x. So I would probably choose to use these two to solve my equation. Now, when I was setting up my equation, I would put the 2x over on the left-hand side, and I would put the x plus 9 over on the right, just because we know that we want our numbers over on the right-hand side, and the 2x doesn't have a constant term. It doesn't have a plus or minus anything in it. So once you set up your equation, you know you want to get your variables over to the left-hand side. You're going to go through and solve for x. And I'm going to leave that up to you. Remember, if you have any questions on any of these, please let one of us know and we'll be happy to help you. Now, your last slide here is your mastery ticket again, and you will see this on your 3D Game Lab assignment, so you don't need to copy this down at this point, but you're going to have two questions using the theorems that we talked about today. So it could be any one of the four theorems. Just be careful because there's only one of them that is different. In all of the theorems, you are setting the two pieces equal to each other with the exception of one theorem, and that is the angles of an equilateral triangle. If you have the angles of an equilateral triangle, they are equal to 60 degrees.